Hey there, this is Chipmunk Math. I'm Vince, and in this video we're going to find out about the idea of Pythagorean triples. So, say that we're trying to solve for the unknown side in this right triangle. We've got this unknown hypotenuse c, and we're trying to figure out what is its value. Well, we set up a squared plus b squared equals c squared. Our two legs are 3 and 4, so we've got 3 squared plus 4 squared equals c squared. We work this out, 9 plus 16 equals c squared. Put those together, we get 25 equals c squared. Take the square root, root 25 equals c. Hey, root 25, well that's just 5. Oh, how nice. What a clean, round answer. In fact, not only was the answer clean, not only was C a nice round number of 5, 3 and 4, the legs, all of the sides, they were all these nice, clean, round numbers. Now, this idea of having all clean, round numbers for all of the values around a right triangle, that is called a Pythagorean triple, a triple of numbers, right? So we define a Pythagorean triple as a set of 3 whole numbers a, b, and c, such that a squared plus b squared equals c squared. The most well-known example is the one we just saw, a 3, 4, 5 right triangle, where 3 squared plus 4 squared equals 5 squared, right? That's why 3, 4, 5 is a right triangle, is because 3 squared plus 4 squared equals 5 squared. Now, there's not just a few of these, there's actually infinitely many Pythagorean triples out there. So there's a whole bunch of Pythagorean triples. Let's look at some of the small ones. First few of them, 3, 4, 5, 6, 8, 10, 5, 12, 13, 9, 12, 15, 8, 15, 17. It can kind of seem, that they're just random, right? They're just numbers, they're just being plucked that happen to work. And to some extent that's true. They do just happen to work, but there actually is a pattern going on in this one here. Let me highlight something for you, right? We look at this and we go, oh, 3, 4, 5, 6, 8, 10, 9, 12, 15. What do they have in common? They have in common that those are all multiples of each other, right? 2 multiplied by 3, 4, 5, that gets us 6, 8, 10. 3 multiplied by 3, 4, 5, that gets us 9, 12, 15. Now, the other ones, the 5, 12, 13, the 8, 15, 17, they aren't connected to this 3, 4, 5, but for these ones that are multiples of it, we'd call that 3, 4, 5 a primitive Pythagorean triple because it allows us to generate the other ones through multiples. Now we'll come back to this idea of multiples with Pythagorean triples in a little bit, but first let's talk about what is this stuff used for, right? It's neat, it's definitely neat and interesting, but is it useful to you? Well, I've got just one word for you. Are you listening? Tests. Right? Tests is why you care about this thing. It is interesting. I think math is beautiful, but the most useful thing you'll probably find out of it right now is that it's really useful for tests. So think about math teachers love clean answers. They love these nice round answers that come out. And a Pythagorean triple, well, they're based on these nice whole round numbers. So Pythagorean triples give you the chance to have those clean answers, and because of that, they show up often on tests, especially on standardized tests, right? Like the kind of tests that they use for college admissions. So if you know those first few triples, it can give you an edge on tests, and that can be especially useful when you're tackling those standardized tests, right? Tests like the SAT or the ACT, those kind of tests you take for going to college. It'd be really useful to have even a minor gain in speed, right? 30 seconds a minute. That can make a real difference on those kinds of tests because they have so little time going on already. It can be really helpful to be aware of these Pythagorean triples just to speed you up a little. So let's see, how can it speed you up? So here's a quick example. Say we've got this one where we're trying to find out what that unknown leg x is, right? We know one leg's 6, we don't know the other leg, and we know that the hypotenuse is 10. Well, if we were doing this without triples, we'd set up x squared plus 6 squared equals 10 squared, right? So that would probably take, 30 seconds, maybe a minute to solve, depending on how fast you are doing this, how much experience you've had with Pythagorean theorem problems, how fast your mental math is. So that's a reasonable benchmark. It's not too bad. But what if you know your triples? Well, if you know your triples, you might go, oh, 3, 4, 5. Well, that's a basic Pythagorean triple. Oh, if I just multiply by 2, I get a 10, a 6, and what's the one that I haven't used so far in that triangle? The 8. The 8 has to be the value for x, right? So if you know your Pythagorean triples, that probably takes 15 seconds, maybe 5 seconds if you're really fast with your Pythagorean triples. Now, that's not a huge gain, right? We're talking somewhere like 15 seconds, 30 seconds faster than if you'd done it with the Pythagorean theorem of a squared plus b squared equals c squared. But once again, if you're on a standardized test, maybe the 15 seconds, maybe 30 seconds really counts. That can add up if you've got a few of these problems. That could really help give you a chance to get one more problem done and give you a little bit of an edge. All right, so let's see how you can speed up with a slightly more complicated example. Say that we're trying to figure out what the value of x is for this right triangle. And now if you've already done the practice problems, you'll notice that this is practice problem number 4 that we're looking at, trying to solve for this value of x. So we look at this and we go, okay, x minus 3 is one of our legs, 12 is the other leg, and the hypotenuse, that's got to be x plus 5 because it's opposite that right angle. So if we're going to set up with a squared plus b squared equals c squared, we plug everything into its place. We've got the quantity x minus 3 squared plus 12 squared equals x plus 5 squared. If you want to see how to solve this sort of thing out, you can check out the practice problems. We work through it there in this Pythagorean theorem, a squared plus b squared equals c squared, an algebra kind of way. And, to do it this way isn't terribly hard. You can get through it, but it'd probably take you, maybe a minute, maybe 2 minutes, depending on it. It's a more difficult one to do than the one that we just saw a few moments ago. So how could you do this with triples, right? If you do triples, you ask yourself, okay, what sides do you know? You see the side of 12. You don't know really what the other ones are, but you see the side of 12. So you ask yourself, what triples involve a side of 12? So you think back to the triples that you've memorized by that point, and we haven't done that yet, but we'll talk about it a little bit later on. So 5, 12, 13, 9, 12, 15, those are triples that involve a side of 12. So at this point, you just got to pick one and run with it just to try things out. And so you choose 5, 12, 13, right? You pick one at random and you see what happens. So 5, 12, 13. So notice the 5 and the 12, those have to be the two legs. You already have the leg of 12 appearing, so it's got to be the case that the other leg, x minus 3, that has to equal the 5. So if x minus 3 is equal to 5, then that implies that x equals 8. Now, don't think that you've solved this right. You don't actually know that x is equal to 8 for sure. This is just a guess that if it's a Pythagorean triple, and if you happen to be lucky enough to pick the right one, then it would be the case that x is equal to 8. So really, you got to check yourself out at this point. You check your x equals 8. Does that work? So let's check with the hypotenuse, right? The hypotenuse, x plus 5. So we plug into that. We have 8 plus 5. So what is 8 plus 5? That's 13. 13. Great. So that means we've got the 12, we've got the 13, we've got the 5. It is a 5, 12, 13. That Pythagorean triple works great. So it must be the case that x equals 8. Everything checks out. We're all done. So we talked earlier about how multiples of Pythagorean triples are also Pythagorean triples, and it turns out this is always the case. If you have a Pythagorean triple, then any multiple of it is also going to produce a Pythagorean triple. Now this idea is connected to the concept of similarity, which we talk about in a different lesson. If you're interested in getting a gut understanding, a gut feeling for where this is coming from, why this has to be the case, I'd recommend checking out that lesson on similarity. It's pretty interesting. But let's actually go and prove this through algebra, that if you scale a Pythagorean triple with some factor, your multiple always has to be another Pythagorean triple. So we start off with our given. We have that there is some triple A, B, C, right? We start off with some triple of A, B, C. We don't know what the numbers are, but we know that we've got some sides A, B, and C that produce a triple. And our claim is that if you come along and you multiply by some K, right? You get some multiple of K and you multiply out and you have KA, KB, KC. We're claiming that KA, KB, KC is also a triple. So before we move on and try to actually prove this, let's think a little bit more about what does that given tell us? That given tells us if ABC is a triple, well, really that's just a way of saying a squared plus b squared equals c squared, right? That was the definition of what it meant to be a triple. And now let's go back and think about what's our claim? Well, if Ka, Kb, Kc is our triple, right? That's what we're going to claim. Really, that just means that Ka squared plus Kb squared is equal to Kc squared, right? That's what a triple is. So our goal here, the thing that we want to show, is that given a squared plus b squared equals c squared, right? Given some triple of a, b, c, it is our goal to show that Ka squared as a quantity plus Kb squared as a quantity is equal to Kc squared as a quantity, right? That Ka, Kb, Kc is also a triple. All right, so let's get started on that proof. So to do this, let's just consider the left-hand side of that thing we're trying to show, right? Just consider that it's an expression of quantity Ka squared plus quantity Kb squared. And let's just kind of see where this goes, right? Let's play with it and see if we can get something to happen, right? So let's put that squared onto each piece. Now we've got K squared A squared plus K squared B squared. Now notice since both of them have a K squared, you can pull that K squared out, right? Sort of like reverse distribution. Now we've got K squared times quantity A squared plus B squared. Hey, a squared plus b squared, remember we had ABC as a triple, a squared plus b squared equals c squared, so we can do substitution and we can swap that out. Now we have k squared times c squared. K squared times c squared, so we've got k squared c squared, and just like we did at the very top, we can pull that squared out as a parentheses, and we have kc as a quantity squared. Okay, so notice every single one of these lines, every single one of these steps was equivalent to the preceding one. So what this means is that bottom line of quantity Kc squared is equivalent all the way back up to the top of where we started, quantity Ka squared plus quantity Kb squared. Therefore, we have that quantity Ka squared plus quantity Kb squared is equal to quantity Kc squared, exactly what we wanted to show in the first place. Therefore, we've proven that if we've got some triple ABC, it must be the case that the scaled multiple triple Ka, Kb, Kc is also going to be a Pythagorean triple. Awesome. All right, so at this point we see that you can scale by any whole number for another Pythagorean triple, right? If you have some known triple like 3, 4, 5, then you could scale by any number you choose, right? Say you multiply by 100 on all of them, then you now know that there's another triple 300, 400, 500. But you don't even have to stick with only whole numbers. You could scale by non-whole numbers. I do have to point out though that the result you'll get won't actually technically be a Pythagorean triple anymore. It's just going to be a right triangle, right? A Pythagorean triple actually has to be based on whole numbers. That was part of its definition. So if you scale by something that's not a whole number, you produce something that won't have whole numbers, and this isn't a Pythagorean triple, but it is still going to be a right triangle. So you can scale by any number you want to produce right triangles, even if they're not technically going to be Pythagorean triples. So once again, say we've got a known triple like 3, 4, 5, and we choose to multiply by, I don't know, 0.9. So that results in 2.7, 3.6, 4.5, and while it's not necessarily, it isn't a Pythagorean triple, but it is going to be a right triangle. We can be sure that those sides make a right triangle. We can keep going with this. We can multiply by something that's not just decimal, but we can multiply by an irrational number like root 7. So 3, 4, 5 would become 3 root 7 times, 3 times root 7, and then 4 times root 7, and then 5 times root 7. Those are the three sides. We can also multiply by pi. 3, 4, 5 becomes 3 pi, 4 pi, 5 pi. All of those things are right triangles. Pretty neat. So say that you want to actually memorize these Pythagorean triples. Well, what are they? Well, here's the first of the Pythagorean triples that are all under a hypotenuse of 100, where all the hypotenuses are less than 100. You get all of these guys, right? There's a whole bunch of them. And I hope that your response at this point is, oh man, that's a lot of things to memorize. I don't really want to memorize that many things, right? That's kind of what I think the response should be. You should think, is it really necessary for me to memorize all those things? And the answer is no, it isn't really that useful to memorize all those things. The thing that you want to memorize is these 4 guys. These are the triples that I'd really recommend memorizing. 3, 4, 5, 5, 12, 13, 8, 15, 17, 9, 40, 41, with 3, 4, 5 being the most important one by far. You can go back and you can memorize those other ones as well, but these are the ones that are most important if you're going to be taking a standardized test. In addition to memorizing these 4 primitive Pythagorean triples, you should also probably familiarize yourself with their multiples, right? 3, 4, 5 has multiples like 6, 8, 10, 9, 12, 15, 12, 16, 20. You get multiples for the other ones. 5, 12, 13 give us 10, 24, 36. 8, 15, 17 would get us 16, 30, 34. And it's not necessary to memorize these multiples because you can always go find out what their values would be just with a little bit more thinking and multiplication, but it's good to have them sort of in the back of your head so you might recognize them if you saw them somewhere in a test, so you can go just a little bit faster, but don't really worry about memorizing all the multiples. Finally, while Pythagorean triples can help you, there are some things that I want you to keep in mind when you're trying to work with them. First off, not every problem uses a Pythagorean triple. It can be tempting, especially after you've been studying Pythagorean triples for a while, to think that every time you do a Pythagorean problem, you're going to be able to use a Pythagorean triple, but that's not the case. Sometimes you're going to actually have to break down and use the Pythagorean theorem. You're going to have things that don't come out as these nice whole round numbers. And they do show up a lot on tests, but it's still not a guarantee that they're going to be on every problem on a test, right? They show up really commonly on standardized tests, but you still might get thrown a problem where you actually do have to break out the Pythagorean theorem and solve for things with a squared plus b squared equals c squared. You won't just be able to recognize it as a Pythagorean triple. Similarly, I don't want you to assume that triangle sides are always whole numbers. There are lots of Pythagorean problems out there that require you to use stuff that doesn't come out nice and round, right? So don't think that just because Pythagorean triples make up some problems that all of them have got to come out being nice round whole numbers. Another thing I want is just for you to not stress over memorizing lots of triples. There are unlimited triples to memorize out there, so it's kind of a waste of your time to try to memorize a huge number of them. Just focus on those 4 ones that I said were the core triples to memorize, and maybe if you want, you can memorize a few of the other low triples, but generally it's more useful to just have a decent sense of the core ones, have some familiarity with the multiples, and that's pretty much enough, because really, you can always go out and use the Pythagorean theorem. Right? Knowing them gives you a bit of an edge. It can speed you up by 15, 30 seconds, but it's never necessary. There's always the Pythagorean theorem. It's always possible to do these problems with the Pythagorean theorem. So don't think that you have to know the Pythagorean triple. It's just that sometimes it can make you a little bit faster, but it's never a necessity. And finally, most important of all, remember that Pythagorean theorem. All this Pythagorean triple stuff is neat, but the core of it all is knowing that a right triangle means a squared plus b squared equals c squared. All right, that wraps things up. Thanks for watching, and don't forget to check out the other videos on this topic over at chipmunkmath.com. See you next time.